Hello and welcome. My name is Keith G. Mills. I'm a PhD candidate at the University of Alberta, and today I will be presenting the paper Building Optimal Neural Architectures Using Interpretable Knowledge, accepted to CVPR 2024. So to start off, let's talk about what we're doing. We're doing something for you. Say you have a real-world task like AI image generation or segmentation, and you want an efficient neural network model to execute this task. What does that model look like? Well, depending on whether you have a transformer or a convolutional backbone, you would have a lot of choices at your disposal when designing this network. So many choices, in fact, that if you construct a search space of them all, it could be very large, easily exceeding 10 to the 19 architectures, and thus it is intractable to exhaustively enumerate them. In literature, the generally accepted approach for this problem is AutoML, Automated Machine Learning Neural Architecture Search, which attempts to smartly navigate the search space in order to find high-performance architectures. However, we think a problem with using NAS is that you are considering the whole architectures, just trying to smartly navigate the search space, and there's just too many overall architectures. And we wonder if there's actually a different way to fundamentally approach the problem that is better. And we answer in the affirmative with AutoBuild. The broad idea behind AutoBuild is we consider the search space modules rather than the whole architectures. Modules could be stages like CNN stages or block structures like ResNet and attention blocks and Stable Diffusion UNets. And the key idea is that there are far fewer modules than there are whole architectures because the modules combine together to form the architectures, as it is a combinatorial. The size of the search space is combinatorial based on the number of modules you have available. And what exactly we do is that we will enumerate over all modules. We will rank them according to some objective, let's say accuracy or accuracy with some latency constraint. We will decide which ones contribute to that objective and which ones detract from it. We will filter out the modules that do not contribute to our objective and only construct architectures from those that do. This allows us to focus on very specific regions of the search space and find very good architectures for that region. However, a challenge is that we do not have labels for individual modules as they exist in combination to form the whole architectures. We do have end-to-end metrics like accuracy or latency for these architectures, though. And so what we do is we cast the architectures as graphs, annotating them with their end-to-end performance, and then we train a GNN predictor to predict that performance. And the key idea is that we have, graphs contain nodes. Each of these nodes has an embedding, HV, and they can be averaged together to form an embedding for the entire architecture, HG. Moreover, we leverage the neighborhood property of graph neural networks to say that HV does not just simply represent a single node, it represents an entire subgraph module itself. We then introduce a constraint that if one architecture has a higher label than another, the norm of that architecture's embedding should be higher than the norm of the other architecture's embedding. And leveraging this constraint with this equation, I would encourage you to look at the paper to see the full details, but essentially what we are doing is we are forcing the GNN to decide which subgraph modules contribute to our end-to-end performance label and which ones detract from it. And that allows us to label the individual modules themselves and rank them, therefore. In terms of results, we use AutoBuild to augment neural architecture search by restricting the size of the search space. And on MobileNet version 3, we have an accuracy, latency Pareto frontier here. We're able to achieve better performance than the 3 baseline methods we consider. There are further results in the paper, not just for GPU latency, but for different devices and search spaces as well. However, a more interesting result is on Stable Diffusion for in-painting. We designed the search space ourselves, and it only actually contains 800,000 architectures. Because this is a tractable amount to consider, we can use the gold standard, which is exhaustive search that globally iterates across the entire search space and tries to find what it considers to be the best architectures. However, AutoBuild is even able to beat the exhaustive search in this scenario by finding architectures that are better at minimizing the FID score compared to the exhaustive search. And in terms of visual results, we have this original image here that we want to basically get rid of this tree structure and paint it out. The architecture found by exhaustive search does a decent job of doing it, but it's not that good in terms of like this structure right here. Whereas the architecture found by AutoBuild more faithfully paints out the tree and is more faithful to the original image. So that brings us to the end of our presentation for building optimal neural architectures using interpretable knowledge, and I hope to see you in Seattle. Thanks. Peace.